Good afternoon. My name is Frank Wood, and I have the distinct honor and privilege of introducing the next tutorial given by Josh Tenenbaum and Vikash Manzika. Before I do that, I have two orders of business to discuss and share with you. The first is that from the conference organizers, it has become apparent that left out of the program is the fact that there will be opening remarks at 5 p.m. So immediately after this, in the area A, you can come and hear remarks from Terry, the general chairs, and the program chairs. So again, at 5 p.m. after this tutorial, in area A, there will be a number of remarks, the opening remarks for the conference, in fact. The second thing that I want to share with you is the organization of this particular tutorial, which will be 1 hour from Josh, and then 1 hour from Vikash. They ask that questions are held until the end. There will be 15 minutes for questions at the end of their 2-hour tutorial. And when you have the questions and want to ask the questions, please come to the microphone so that everybody can hear your questions. Okay, so 2 hours, then 15 minutes for questions. Now comes the fun part. Josh Tenenbaum and Vikash Manzika are both MIT professors. Josh is a professor, sorry. They're both at MIT. Josh is a professor in the Department of Brain and Cognitive Sciences, CSAIL, and the Center for Brains, Minds, Machines, where he leads the Computational Cognitive Sciences group. Vikash is a research scientist and director of the Probabilistic Computing group. Both of them have contributed actively to multiple areas of machine learning and AI, as well as cognitive science. They were some of the early pioneers of universal probabilistic programming for AI in functional languages, as co-creators of the language Church, among other things, along with Noah Goodman, Dan Roy, and Keith Bonowitz, and have helped build a community around probabilistic programming for AI by co-organizing several NIPS workshops and many, many other activities. They've been foundational to my work, and I know, like the rest of you, I look forward to a fantastic tutorial from the two of them. So, Josh, come up and take it away. Thank you very much.
Okay, whoa. Thanks, Frank, for that great introduction. Thanks, everybody, for coming. It's a great honor and pleasure to be here and tell you about the things we've been thinking about and working on for a few years. So as Frank mentioned, both Vikash and I, the work that we do and the work with our colleagues really sits between science and engineering. I would say I'm a scientist first and foremost, a cognitive scientist, and my chief interest is in trying to understand the basic nature of intelligence in the human mind and brain, just that. But my kind of science, and I'd say our kind of science, is a reverse engineering approach. So we want to understand how the mind works in the language of engineering, and then that should have all sorts of payoffs and all sorts of ways to test it by trying to build more human-like intelligence in machines. So what we're going to talk about today, especially my part, is really going to be sort of sit between cognitive science and AI. And I think you'll also see those themes in Vikash's part, although his will be more of an engineering focus to the science focus that I'll be having here. Now, I think we all realize, this is a golden age for machine learning, for AI. It's an exciting time to be doing this kind of work that sits between the science and engineering of intelligence because of the scale that AI is with us now. But I think it's also fair to say, and this motivates a lot of our work, that while we have many exciting AI technologies, we don't have any real AI. What I mean by that is we have systems that do things that we used to think only humans could do. Now, machines do them incredibly well. And yet we don't have anything like the flexible general purpose intelligence that each of you use to learn to do all of these things when you need to learn to do them. So each of these systems was engineered by fairly large teams of experts working for a long time at a cost of many millions of dollars in some cases. And each one just does one thing. So AlphaGo beats the world's best, but it can't drive to the match or tell you how Go works or even tell you that Go is a game. So what's missing? What would it take to engineer in machines that kind of general purpose human intelligence? Now there's many things that are missing, okay? But the basic idea that motivates what we're going to be talking about here in a lot of our research is this. Recent AI technologies and machine learning successes are mostly a story of pattern recognition, right? Neural networks, deep learning is the most recent version of that, but really the machine learning success story, which we all know at NIPS is not just about deep learning, is a story of taking pattern recognition from the textbooks to the real world on a grand scale. But intelligence is more than that. Intelligence, as we like to say, is about modeling the world. It's about explaining and understanding what you see. It's about being able to imagine things that you've never seen but might want to, and then making plans and solving problems to make those things real. It's about learning as building new models, refining, recombining, maybe even synthesizing whole new models as your experience in the world grows. So we'd like to understand how to capture these model building abilities in engineering terms. Now, I think it's fair to say that we are not close to being able to do that at the scale that, say, we can do pattern recognition now. We're decades away, and I say decades with an S carefully. It's at least a decade, I would say, maybe many more, before we can understand the human ability to model the world so flexibly, so richly, so quickly in engineering terms on the scale that, say, a big company or a hot startup could use the way we now use deep learning or other pattern recognition technologies. Yet I think it's also fair to say, and very exciting, that we're beginning to make progress. We're beginning to understand some of the basic principles, computations, mathematics, engineering motifs, and tools. And we're going to tell you about these early steps right now in two main areas of intelligence: common sense scene understanding and the idea of learning as model building. So in the first topic, we mean something like, how do we see when we look around the world not just patterns and pixels, but a whole world of objects and agents, other minds, and our own ability to act and interact with those objects and other people, what we like to call intuitive physics or intuitive psychology. And then learning, well, again, today's conventional machine learning systems might take hundreds or thousands of examples to learn a new concept or a new function. And yet humans can often learn these things from just one or a few experiences. How does that work? Or how might we learn a new skill or a new task, like a new game, or how to use a new tool in just a minute or two? The plan, as you already heard from the tutorial, is really basically two parts. I'm going to talk about what's the basic idea in intuitive terms, motivated by cognitive science, and some examples. I'm going to try to explain at a high level what are probabilistic programs, why do we want them for building more human-like AI, and something about what are their interfaces with the rest of the AI toolkit. And then Vikash is going to consider the really important question of, can we actually get this to work? So how do we work with probabilistic programs more formally and systematically in probabilistic programming languages? And what will it take to get these things to work and scale in the real world? And another important theme here, and to me, if you this is one of the key take-homes, if you want to say, what are probabilistic programs, why should I care? Well, I think it's fair to say, when we survey the entire AI landscape, the history of the field, there have been three big ideas which have really proven their value across multiple waves of ups and downs of excitement. Okay. I would say one of them is the idea of probabilistic generative models, which includes Bayesian networks and every other kind of graphical model, in order to capture the causal structure of the world and deal with uncertainty. The idea of intelligence as symbolic processing, okay, which includes programming languages or first-order logic systems. If you saw the last tutorial, various logic programming approaches, but any programming language really is a testament to what is really the oldest good idea in AI, that intelligence is some kind of symbol manipulation. And then, most recently where a lot of the excitement has been is around neural networks or neurally brain-inspired architectures for, again, mostly pattern recognition and other such things. And one way to think about probabilistic programs, increasingly, it wasn't always like this, but when we started working on this, and I think when Frank started working on this, we thought, much like in the previous tutorial, we thought, okay, we're trying to combine the best of those first two bullets. The probabilistic graphical models toolkit, especially the causal ones, the idea of directed causal models, and symbol processing to be able to scale towards richer kinds of causal knowledge and compositional languages. But increasingly also neural networks have become a central part of the picture. And I think these days the modern landscape of probabilistic programs and probabilistic programming languages is one of the most exciting places where these three big AI themes interweave in increasingly exciting ways. This is just a figure here from a review paper that Zubin Garmani had a year or two ago in Nature, just kind of roughly contrasting a traditional directed graphical model, like for sort of state estimation and control, with a probabilistic program description. And again, at a very high level, you'll see much more of this, especially in Vikash's second part of the talk, but at a very high level, think about all the kinds of things that you'd like to do with a causally structured generative model, but now say, how do we capture processes in the world that don't just fit into a graph, where we need the fine-grained control and expressiveness of a programming language, data structures and algorithms in the loop of our causal models. And then increasingly, again, how might we use neural networks, for example, to dramatically accelerate inference or to extend our models into non-parametric regimes. So that's sort of a high-level summary of how the work in this tutorial fits into the modern AI landscape. Now let me turn to common sense scene understanding, the first of our big application areas, or just places where we're trying to understand what is that common sense, flexible, general purpose stuff inside your brain. We mean the ability that you see for yourself when you look at scenes like these on here. The ones on the left illustrate what we call physical scene understanding or intuitive physics. The ones on the right, more intuitive psychology. Look at these scenes and don't just recognize and detect objects, but for example, on the left, see what's likely to happen or what you could do, what's dangerous, how you might act to prevent danger. So you can see the table is supporting some objects. If the table were moved or bumped, some of those things might fall. Or you look at the house being framed, and you can see that there must be brackets or nails or something holding those pieces of wood together, even if you don't know exactly where they are. You certainly can't see them in the image. They're less than 1 pixel, and yet you know they're there, or the whole thing would be falling over. Or that stack of dishes taken in my local cafe. As the barista said, which caused me to snap that photo, he said, that's an accident waiting to happen, or I think it might have said disaster. Okay, it's minor disaster if you tried to pick that up to bust the dishes without restacking them and all go falling onto the floor. So how do you judge the stability of a bunch of complexly shaped objects just stacked up like that? Or the scenes on the right. You don't just recognize people and see that they're engaged in some kind of joint activity, but you have a sense of what's going on inside their head. What they want from the other people in the scene, what they think about the scene, what they might think about what other people are thinking or wanting. So look at that crossing guard down in the lower right. And you see she's holding up the sign, she's making eye contact, presumably with a driver. So what has to be going on inside her head, knowing those kids who are crossing behind her? She's looking to see if that driver has seen her and made eye contact. That's what we mean by intuitive psychology in natural scenes. You can see all this at work, not just in scenes like those, but in much simpler kinds of scenes. Just think about kids playing with toys, playing with blocks, playing with each other, playing with blocks. This, to me, is very inspiring. As a scientist, when I talk about common sense, I mean the kind of basic intelligence you see, not just in these, say, 2- or 3-year-old children, but in the babies that you see over there on the right. I'll show a couple of movies in a bit. Ways in which even a 1-year-old or a 1.5-year-old has more basic grasp of the situation they're in the world and the other people than any machine or robot that's been built. So let's take a look at this kid here, the first one. These are just a couple of videos from YouTube. This is a 1.5-year-old. And what you can see he's doing here is he's doing something that lots of kids like to do, stacking up cups, right? You can see he's got 3. He's trying to fit the 4th one on. I won't take up all of our time just watching the whole video, though it's very exciting. But you can see he's trying to get the 4th one on, but he sort of figures. Notice he's trying to make a little substack there. Put the 2 on. We can zoom ahead a little bit. It gets a little complicated because he got stuck the wrong way, but eventually he manages to get the blue one on that other one, moves that thing out of the way, picks it up, and puts it on top of the other. He puts 2 on 3, right? And that's quite an accomplishment. In fact, he's a little happy with himself and claps. That's a sub-goal. You know he's got the large goal of trying to make the whole stack. But that breaking the problem of a goal into sub-goals and pieces, and the idea that it's not just stacking up cup on cup on cup, but you can stack up stacks on stacks. There you see some of the building blocks of symbolic cognition, but superimposed on top of the intuitive physics necessary to manipulate those objects. Again, if you've ever worked with robots or seen videos of amazingly impressive robots, but to do that kind of manipulation of objects and planning is way beyond the current state of the art in AI and robots. Now, eventually he manages to get that whole stack built and is so excited that he puts a little crown on top of it. And again, now that deserves a real hand of applause. Yes, from you too. And that falling down and getting up afterwards, that's also something that no robot could do, as we know. Okay, but maybe in the last year, Boston Dynamics has nailed that one. But it's still the case, with all the progress on the physical hardware side of robotics, that we don't yet have the mind inside the body. Take this younger baby here. This is a 1-year-old. This is one of the internet's most popular videos because it features both a baby and a cat. And here the baby is stacking up cups on top of a cat. He decided, again, think about flexibility. think about, unlike machine learning systems which are trained to perform a certain task, he just decided for himself. I'm quite sure that nobody demonstrated this task to him. He decided, hey, this might be interesting. I wonder what can happen if I put these cups. How many cups can I fit onto the cat? Now watch what happens there when he reaches back to that purple one. That's, to me, one of the most exciting moments of the video, because that purple one that he just reached back for behind himself, he had not seen it or touched it in at least a minute. But yet he still represented it as being there and incorporated it into his plan. Okay, that's a kind of very rich object permanence and, again, awareness of the physical objects in the world. That's quite remarkable. Now, the plan doesn't necessarily go according to plan. So at some point after he's, let's see. At some point he's decided that, right, he can't actually fit the cups onto the cat stably, so he just decides he's going to put them over to their side, and then anyway, everything breaks loose. But you get the idea of the kind of general purpose intelligence that we're trying to capture. I'll just show you one more motivating video here, which is, this is actually from an experiment by two psychologists, Felix Warneken and Michael Tomasello. It's from a little bit more than 10 years ago, and it's one of the most important and remarkable studies of young children in the last decade or so. This is, again, an experiment with 1.5-year-olds, like the age of the first kid. And what you'll see here is a study of the spontaneous helping ability. It's both intuitive psychology, but it shows how intuitive psychology sits on intuitive physics. So the subject in the experiment is the little kid in the back. The experimenter is the big guy, and watch what he's doing and imagine what the kid is seeing. So he sees him kind of banging these books up into a cabinet or something, and it's not really clear what he really has in mind, except somehow he seems like he needs help. So the kid goes over, and what does the kid do? This is the data, right? What does the kid do when the experimenter stops moving? He looks inside, he steps back, he looks up, and notice how he makes eye contact. Here, we'll just watch it one more time. The most exciting part right here again. When he steps back, he looks up and makes eye contact, and then looks down to the guy's hands, right, to see, well, making eye contact, did I get what you had in mind? Did I do the right thing? Did I help you out? To me, this is a grand challenge for AI. If we can understand in engineering terms what goes on inside kids' minds like that, when they see somebody doing something that they've never seen before, they analyze the physics of the situation, right, the force of the thing banging up against the other thing, and the sense of what might be possible goals and what you can see or can't see behind the door, and how you have to act to get from one state to the next, and then the sense of what is the helpful thing to do. I think if we can get that, then we would have made real fundamental progress on the roots of human intelligence. So how are we going to do that? Well, the way we've been thinking about this, and again, this is something that Vikash and I in some form have been thinking about for a number of years, as well as other people in our field, is by defining these probabilistic causal models. These are kinds of probabilistic programs on top of the kind of programs that have been used to model the world in a rich, interactive way in modern game engines. So video game engines, as I'm sure most of you know, are tools that allow a game designer to create a rich, immersive experience, a three-dimensional world that a player can interact with in real time. And the game designer doesn't have to write all of computer graphics, or doesn't have to write all of physics, but the game engine takes care of updating the scene from the player's viewpoint and handling interactions like object collisions or when something might break. I mean, you can turn it and off or write different kinds of special purpose physics. We have soft body physics. Increasingly, we have fluid mechanics, even in some form in game engines. And these tools for producing images and physical interactions that maybe don't really capture the way it actually works in the world, but just enough to look good on short time scales in a real-time interactive loop. We think that's a first approximation of the kind of basic common sense representations of the physical world that are emerging very early in development, like you can see in those babies. And then on the intuitive psychology side, right, we take the same kind of idea and extend it with simple kinds of game AI or planning engines, right? So game engines often also have tools that allow, for example, a guard to patrol a base in some vaguely human-like way rather than just like shooting randomly into space, but to have a line of sight perceptual stream where they only detect a player and believe that a player is there when the player enters their line of sight, and then they form a goal or a desire to go after and take actions like pursuing the player in some kind of reasonably efficient route. Okay, so it's these algorithms for going from 3D scenes to 2D images or graphics, updating the 3D state of the world over time with physical interactions, and then wrapping that inside a planning loop where an agent forms beliefs based on what they can see and plans efficient cost-benefit trade-off actions that we think are the basic kinds of causal models at the heart of human common sense. Now, by wrapping those in the framework of probabilistic programs so that we can, for example, be uncertain about the inputs to some of these programs, observe their outputs, and make good guesses, effectively approximate Bayesian inferences about their likely inputs, and then propagate that uncertainty forward and backwards. That's the basic idea that we're thinking about how to capture this common sense scene understanding. So I'm going to illustrate that mostly in intuitive physics and say a little bit about intuitive psychology. But first, I want to also say one thing about inference. Mostly Vikash will be talking about inference, and I think it's important. And this is a preview of some of the themes in his part of the tutorial. But I think it's important to recognize that what I'm talking about here, and really the probabilistic programming view, has two kinds of programs at its heart. What I'm talking about are the modeling programs, the programs which capture our common sense knowledge. Okay? These compositional, causally structured, object-oriented, maybe recursive if we have minds that can reason about other minds, these mental models. And then how do you actually get them to work? In terms of making inference from sparse data or learning, well, you have meta programs that handle inference and learning. And it's important to recognize that the world of these meta inference programs are going to unfold on different kinds of timescales that might optimize or trade off in different ways speed, reliability, and flexibility. So I've listed here 5 different kinds of activities that really are responsible for the structure of knowledge in your brain, and they unfold on very different timescales, with very different kinds of inference algorithms potentially appropriate for them. So perception unfolds on the timescale of milliseconds, maybe up to a second. Thinking is more like a second to a minute. Learning might be minutes to hours, maybe up to a day. It's important that learning can be consolidated overnight, for example. By development, cognitive development, we mean the things that go on in these young kids' heads over days, months, years, maybe up to a lifetime. There's some things that you're still, learning and integrating about your deep theories of the world, perhaps even at your age. And then, very importantly, evolution, both cultural and biological evolution, which is adaptation of mental models over many lifetimes. Now, in what we're going to talk about, we're mostly talking about perception and a little bit of thinking and learning, okay? Because in many ways, as we go towards these longer timescales, everything gets harder, slower, less reliable, but more flexible, right? We know that evolution is the one adaptive process in the physical universe that actually builds complex structures with complex functions, like our bodies and our brains, okay? But for the most part, we're interested right now in things which happen much faster and more reliably, like perception or learning bits of models. And it's important to recognize that there's a huge engineering tool set, again, which Vikash will mostly be talking about, different kinds of inference algorithms which are specialized or at least better suited for these different timescales of adaptive processes. I'll say a little bit about some of the ones we've been using in the models we build, but for the most part, the general enterprise of trying to understand that whole landscape of inference algorithms and how to put those into an effective programming language for inference is what Vikash will be talking about. Okay, so let's actually look at, say, some of these intuitive physics computations. So here's an example of a setup that's both an experimental scenario we study in our lab, but it's also increasingly the kinds of things that, say, people in robotics are starting to actually have robots be able to deal with. So we'd like to take these blocks here. These are like Jenga blocks. And this study was all done in simulation, but increasingly people are doing these kinds of things, with actual objects. I should say, by the way, this is work that I'm going to talk about that was mostly done in our group starting a couple of years ago, or more than 5 years ago, by Pete Battaglia and Jess Hemrick, both of whom are now at DeepMind. Jess just recently finished her PhD. Pete was a postdoc, and Jess just finished her PhD at Berkeley. And the thing that we set out to do was to try to understand, when you look at a scene like any one of these here, what makes the blocks look, for example, stable or unstable. So hopefully most of you will agree that the scenes in the upper left, the towers of blocks there look pretty stable, and as you move down and to the right, they look like they're more likely to fall under gravity. So how do we account for that sense? Well, I'll show you one example, and we'll talk about a couple of others, because this is a nice case study in which to contrast the probabilistic program approach and a sort of a mental simulation of intuitive physics with, say, a more pure pattern recognition approach. So here's an illustration of the basic idea of our model. Notice there's these two kinds of arrows here. There's the blue graphics arrows and there's the red physics arrows. I showed a little schematic of this kind of model before, and you might say, if you're familiar with the graphical models toolkit, you might say, well, what I'm showing is basically like an HMM, right? A hidden Markov model. There's a latent world state, there's some transition dynamics across time, and then there's some observation function which goes from the latent world state to the observation, which is the image. And in some sense, that's fine, but just talking about it as a graphical model like that doesn't have the fine-grained, compositional, causal, object-oriented structure, what we like to call informally the thick nodes and arrows. That's really what you need in order to reason about the physics of a situation like this. So the way we think about this is we say, well, that observation function is a graphics engine, right? It's some mapping that goes from a 3D object state description, like a simple CAD description, the kind of thing that would be the state of a game physics engine, and then renders that into an image. And perception is working backwards, inverting that graphics arrow. I'll say a little bit about how we do that, although Vikash will say a lot more about that, because inverse graphics programming is one area where the probabilistic programming toolkit has had a lot of success, and also where neural networks are doing exciting things as part of the mix. Okay, but let's just now take it for granted that we can see an image and make a guess about a 3D object description like the one shown in the upper left that is a likely input to the graphics engine that rendered into that observed image. Now then, very conveniently and not accidentally, that same object-based representation is the state of a game physics engine. Again, an engine for approximating Newtonian mechanics, rigid body interactions, but not only necessarily rigid body interactions. In this model, that's all we were doing, but recently we've been extending this in all sorts of ways. But anyway, you have this now an ability to say, forward simulate under an approximation to Newtonian mechanics, but taking into account, for example, uncertainty in the state or uncertainty in the forces just through forward simulation. So here I'm showing you one particle, if you like, one approximate posterior inference of the inverse graphics, and then propagating that, or just running a simulation of the game physics forward, and what you can see is that, well, most of the blocks fall down. Here's another inference particle. It's a different sample from the posterior in the inverse graphics, and then we run physics forward, and again, a slightly different thing happens. I'll just switch back and forth between the two. What's important is that though the same, or the fine-grained state after a few time steps is different, fundamentally the same basic thing happened, which namely most of the blocks fell over. So the model that we build in this model and a bunch of other places takes a few of those samples, takes some average of statistics of what happened, like how many blocks on average moved or fell down to the ground, and uses that as a judgment of how unstable the tower is. What I'm showing you here is one example of a cognitive experiment, or you could call it a user study. On the y-axis, you see the average judgments of a group of people on a scale of 1 to 7, where high means very unstable, this tower is very likely to fall under gravity, and low means very stable, not going to fall at all. And on the x-axis, you see the average of a few of these inference particles in this probabilistic physics engine. And what you can see here is typical of a bunch of experiments that we've done, which is that this approach is able to capture most of the variance, call it the first principle component of human intuitive physics, without really any special tuning. There's a couple of parameters that have to do with the different sources of uncertainty, and as long as there's just at least a little bit of uncertainty, not too much and not too little, basically the model fits about the same. We can't really, from an experiment just like this, determine exactly how much uncertainty is in different parts of the model. Okay. Now we can compare this with a very different sort of approach, a much more learning-based approach and really a much more pattern recognition approach. And I think both of these approaches have their value in scene understanding, but this is an instructive case to contrast and show what might be some of the advantages of this kind of probabilistic program approach. It's important here that there's no learning so far. There might be learning involved in inverting the graphics engine, and there might be learning over a long time scale as a kid builds this physics engine. But at least in this model, it doesn't learn anything task-specific. Now let's contrast that with, here, for example, a nice exemplar of the alternative approach, which is to try to basically turn this judgment into a pattern recognition problem. So here I'm highlighting work from the Facebook AI group. This is work led by Lehrer and Adam Lehrer, and I think the senior author was Rob Fergus. And they were trying to solve a very similar kind of problem to see if they could get a neural network, though, to learn to make judgments of will this stack of blocks fall over. And I think it's, to be fair, right, they were interested in whether you could take fairly off-the-shelf convnet technology and how easily it would be to adapt it to solve this problem. They weren't necessarily working extremely hard just to solve this one problem. But what they found was that by taking basically a pretty standard image convnet giving it a couple of different losses, and I won't go into the details. They were able to train the system from a large number of game engine simulations to predict, will this stack of blocks fall over? And you can see some of their results over here. And I'd say the most impressive thing is that training on simulated data was able to transfer to real data. I'll show you in a little bit some of their actual movies from real stacks of colored cubes, much like the ones you see in the upper left. Okay? And this is, again, one of the key insights and lessons of the last couple of years, is ways in which training neural networks for vision with simulated data can transfer to the real world. And I think there's a deep insight in that that really reflects the ways in which neural networks can be seen as approximate inference for probabilistic programs. Frank has a nice recent paper on that in particular. I would lead you to take a look at that. Okay, but in this setting here, so PhysNet trains on simulated physics data, transfers to the real world. The limitations, though, is that they have to train it a lot. They train it on 200,000 images of 2, 3, or 4 cubes. And they show that it might transfer to 5 cubes, or maybe it was 2 and 4 cubes and they could transfer to 3. So they could get some transfer even within the set of cubes, but still, they're just basically working with cubes, not all sorts of other shapes. And it's just a small number of them, just 2, 3, or 4, and they're basically in that domain. Whereas the system that we talked about, I showed you one example, but in other experiments in the same paper and in other work, the very same system, without any extra training, is able to answer a very wide range of questions about a wide range of scenes. So the blocks can be different sizes and shapes, okay? And the questions aren't just will it fall. The PhysNet paper was just trying to predict will it fall. We might ask, how far will it fall? Which way will it fall? Or what happens if, for example, the blocks are different colors or made out of apparently different material, and we know that one material is much heavier than the other. So in the upper right, if we know the gray stuff is 10 times heavier than the green stuff, it might change your sense of which way the blocks will fall. People change, and the model changes in the same way. It doesn't have to learn it. We just tell it and translate language, effectively, into the parameters, the causally relevant dynamical parameters of the physics engine. Okay? Or we might use it to make inferences backwards, like if we see those red and yellow stacks there that are surprisingly stable, we might infer that the red stuff is 10 times heavier than the yellow stuff, for example, or maybe it's the yellow stuff heavier than the red stuff. Let me show you one other judgment, which is kind of a weird one, unless you haven't done it before, unless you've seen me give a talk on this. But it's designed to highlight the way in which your intuitive physics engine and a probabilistic program can be, without any learning, adapted to answer an endless range of novel tasks, which we think of as queries. Okay, Vikash will say much more in a little bit about what a query is. But here's this weird task. So let's say we've got these red and yellow blocks, and this table is bumped hard enough to knock some of the blocks onto the floor. Is it more likely to be red or yellow blocks? That's the question. And now I'll ask you to respond interactively. So what do you say, red or yellow? Just shout it out. Okay. How about here? You got to shout loudly so I can hear you. Okay. Here. 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 A little more uncertainty there. Here. Here. Okay. Enough. But you got the point. You saw that in some cases, everybody was sure, everybody said the same thing very quickly. In other cases, there was a little hesitation and much more uncertainty in the room. Okay? So how do we explain that? How do we explain your ability to make these judgments, and where does the uncertainty come from? Well, I'll show you at least one hypothesis. So this is a window into a game, one of our simple game engine simulations of one of these scenes. Here you're seeing on the left a small bump. I'm going to play it all the way. Here's a big bump of the same configuration. Notice again, different things happen at the fine grain, but at the level that matters for intuitive physics, the same thing happens, namely all the yellow blocks go over and very few or none of the red blocks do. So it doesn't really matter which bump you simulated. Also, you don't have to simulate at high precision for a long period of time. Just a couple of time steps in each of these cases is enough to see the answer. So we think it's not implausible, both for humans and potentially for robots who want to reason in human-like ways, to be able to do a small number of approximate physical simulations like this in order to figure out what's likely to happen next. And also, as we'll see in a little bit, to plan your own actions. So here I'm just showing you how the very same model predicts judgments basically just as well in this experiment as it did in the will it fall over experiment. But contrast the kind of experience you have, right? Like we've been making judgments about will these blocks fall over since we were kids. But unless you were in this experiment before or saw this talk, you never made this particular judgment. And yet the knowledge that you have about the physical world, we posit, is the same. So you should be basically just as good. You might be a little bit better if you're an expert at stability. But for the most part, it's not about task-specific learning. Now let me gesture a little bit at where neural networks might come into this picture, and Vikash again will say more about this in the next part of the tutorial. Here I'm actually showing the same basically kind of state estimation prediction picture as before. I'm now actually showing the Facebook group's real-world images of these 4 cubes. And this is in particular, I'm highlighting some work that you're going to see in the main conference from Jianjun Wu and colleagues. I think it's a poster in Spotlight 2 nights from now, in which Jianjun, and I'll really show you a couple of different things that Jianjun Wu has been doing recently to try to use neural networks basically to invert graphics. So together with Pushmeet Kohli, who was at Microsoft, this was part of a Microsoft internship, but Pushmeet's now at DeepMind, Jianjun built for a CVPR paper just this last summer, what he called a neural scene derenderer, which was basically a model that was trying to learn to de-render a graphics engine. Here he did it with some very simple ones like the Minecraft game engine, but the idea was to learn to map from images into like a scene XML description, the graphics engine state. And he did a lot of work to make this work. He used some clever ideas from computer vision mid-level representations to deal with occlusion. He used the same idea that, again, I mentioned before and we'll keep using here, which is that the network is trained from simulated data from the graphics engine. So you can think of it as drawing samples from the generative model, and then the neural network gets, because the samples are internally generated, gets to see the right targets for training. It's learning not to do anything in the real world, but it's learning about effectively the patterns of its own posterior inference. Okay? And there's a little bit of top-down Monte Carlo inference, so it's not just purely a bottom-up neural network scheme. Now, in the NIPS paper that Jianjun's going to present in a little bit, he used the same scheme to de-render one of these physical scenes, but then what he calls de-animation and re-rendering. The idea is now you can learn to map very, very quickly from the image into the state of the physics engine, like how many blocks are there, where are there, and then you can do various kinds of physical reasoning. So here what I'm showing you are, on the left, you're going to see the Facebook real-world videos. They're static right now, but I'm going to press play, and you're going to see what happens. Hopefully those scenes look like they should be falling over. And then you're going to see Jianjun's system imagining what would happen. And again, it's actually re-simulating the movie in a simple approximate game graphics engine. So here we go. I'm going to press play. Think for yourself what's likely to happen. How are those blocks likely to fall? Okay. Again, on the left is what actually happened. On the right is one of our model's probabilistic forward simulations. I'll show it one more time here. And you can see that it's not exactly right? It gets the timing wrong for the one on top, although it's pretty right on the one on the bottom, and the direction's a little bit wrong. But it's usually mostly right. It's usually right about whether it will fall or not, and the approximate direction up to about 30 degrees, which is basically what people are good at too. Okay, so here's couple other examples. Again, think about how it's going to fall. Some of these ones, like the one on the top, is really obvious, it's very strong, and the model gets it exactly right, just like people would. Here's one more scene. These ones are a little subtle because of how depth works in the scene, but again, the model is able to basically get it. And again, because the state of the model is based on objects and forces, you can naturally do things like this. Like you can say, well, what would happen if, right? It's not just about recognizing patterns in data, but you can say, suppose there was a wind from the right, or somebody bumped the top block from the left. You could imagine how the blocks might fall when they wouldn't otherwise fall. Or down in the bottom, you see the scene is unstable, and you ask, what force could I apply to keep it up, right? So again, these models support imagination, explanation, and planning. Now let me just say a little bit about intuitive psychology, and then a little bit more about model learning. I'm not going to say nearly as much about intuitive psychology as about intuitive physics, but just to set up a couple of the things you'll see from Vikash. We can extend this kind of idea to say now we're looking not at an inanimate object, but at an agent. So here's some work that Chris Baker did in our group a couple of years ago, about 10 years ago now, and where people are watching an overhead scene of an agent moving around in a room with obstacles. There's one of several possible goals, marked A, B, and C, and over the course of the dynamic path, again, imagine an overhead scene, people are asked to judge how likely is it that the agent's goal is one of those things. And what you can see down in the bottom is just a few data points from a couple of these scenarios. There's close to 100 in the actual experiment. But what you can see is subtle dynamics. First you think it's this goal, then you think it's that goal. Things go up and down. And you've got the middle row is people's judgments, and the bottom row is our model's judgments. And again, the fit is almost perfect. The correlation is even higher for this intuitive psychology than for intuitive physics. Again, the model doesn't involve any real learning, right? It just has the basic mechanics of rational intentional action that says you get a high reward for getting to your goal and there's a small cost of action, but I don't know what your goal is. And maybe I don't know exactly what your cost is, or maybe I don't know exactly how likely you are to always do the right thing. Then can I make an inference by seeing you move in the world? What is the most likely interpretation of why you did what you did? Going forward, we'd like to extend this, and this is work that's sort of in progress on both the psychophysics side as well as the AI side, to scenes that are actual real-world scenes of people reaching in the world. So here we can try this again as a interactive demo. You're going to see this woman reaching for one of these 16 objects on the table in front of her. You see that 4x4 array. And raise your hand when you think you know which one she's reaching for. Okay, so here we go. It's going to play in slow motion so you have some time. Raise your hand when you think you know. Okay, yeah, so there we can stop. So what you might have seen, what I saw, is actually hands went up pretty quickly, although then there was some hesitation because they weren't quite sure and a little bit of laughing, and then they all shot up. Much like that dashed line that you see there, right? So that dashed line is actually the predictions of our model. It's not human data. We're currently in the process of testing this. This is work that Tao Gao and several colleagues are doing. Okay? And the way the model works is, again, it basically takes a fairly state-of-the-art, at least in simulation robot motion planner. This is the Mujoko physics engine. And it's trying to say, imagine hypothetically each of the possible goals, what would be the most physically efficient reach that the person would take? And then to try to see how well does each one of them explain what you see. And what you can see in this movie is all those simulations in parallel, and the blue bars are the posterior probability. Now, we think in principle this is a reasonable way to think about what your brain is doing, right? In practice, we think that this, the inference here is slow and intractable. And again, what Vikash is going to show you is some of the initial steps in probabilistic programming languages that people, in particular in his group, are taking to try to make these kinds of inferences much more efficient in a way that might plausibly be like what's going on in our brain at the mechanistic level, as well as what we want to put into a robot. In case you're wondering, why go through so much trouble just to say which thing is someone reaching for? Well, again, think about how human action is not just moving along short paths in easy joint space, right? So think here, for example, now the same woman is going to be reaching for an object, but she starts in a sitting position. And watch, and notice that even before she starts to really move her arm, you have a really good idea of which thing she wants. It's one of these ones over here, right? Just because of how she had to move her body and where she's looking. Or look at this scene here. Just right now, just the fact that she moved up and started going along this side of the table already tells you that it's probably one of these things. If it was one of these ones, she would have moved the other way. If it was one of the close white and blue ones, she wouldn't have had to get up, right? You know that without having to even reason through it. Or take this scene here. This is Tao Gao. Notice that he's going to be reaching in a somewhat unusual way, and try to figure out what he's doing. So what's he doing? Anyone have an idea? Why is he not just reaching in a straight line? Yes, I heard the word glass, right? He's reaching over a piece of glass. Can you see that? Can anybody see the glass? Yeah, okay. But you see the glass in the sense that you know it's there, right? You don't actually literally see the glass, right? I think it's highly unlikely that a computer vision would be able to recognize just on its own that there was a piece of glass there, because it's literally almost invisible. And yet we know it's there. We basically see it because we understand that humans move along efficient paths, and you're doing a joint analysis of the action in terms of his goal and his perceived constraints on it. Okay? We know that glass is something that you can see through but not move through. So these are the kinds of things that we're just beginning to be able to actually put into probabilistic planning programs that, again, can be inverted to make these kinds of inferences. And just the last thing I'll show you about intuitive psychology, we'll take these scenes here where now there's multiple agents. So the scene on the top looks like somebody is helping somebody else, right? And the scene on the bottom doesn't look like helping, but maybe something else, right? kind of hindering or competing. So how do we capture those concepts? What makes it look like helping or hindering? Well, here our idea is to take these agent planning models, these simple ones, and recursively extend or embed them to have agents whose utility functions, right? In each of these cases, it's all about utility analysis. Have agents whose utility functions depend on their expectations about another agent's expected utility. And if that's a positive dependence, we call that helping. If it's a negative dependence, we call it hindering, right? Or trolling or something like that. Okay. Subtleties like that would be missed by this algorithm. But you can start to see why we might want to have agent models that we can embed in a programming language with a little bit of recursion and abstraction. And we think this is the kind of thing that's going to be necessary to achieve that ground challenge, to be able to build scene understanding systems that can do like what that kid is doing there. Now, in the last few minutes, I want to turn to learning. Okay. Now, we might ask, well, okay, I talked about how this system doesn't have to do any task-specific learning, but we might ask, what kinds of algorithms could build this knowledge over the course of, say, the first year of a kid's life, as we seem to observe? And I think it's important to recognize that this is a very different kind of problem when most people are talking about machine learning, right? All the things that make neural networks nice, or several of the key things, right? End-to-end differentiability with a smooth optimization landscape. If we're talking about learning programs, which is what we're talking about, that doesn't seem likely to be there, okay? What we're asking effectively is, can we build program learning programs? And we think that we can, okay, at least in very small limited cases. I'll show you one example of that. But to actually build systems that can do this, we have to recognize, I think, that it's very hard, and a lot of the adaptation is going to unfold over those much longer timescales I talked about at the beginning. So, for example, evolution, all right? It's really an open question how much of this architecture at a high level might be built in and how much is learned. But let's talk about the ability to actually capture learning programs as itself a kind of probabilistic program or meta program inference. And I'll say a little bit about this in the context of learning concepts from very rapid, small sets of examples. I'm going to talk about some work that maybe many of you know. I've talked about it at NIPS before. And it's helped to kick off, a fair amount of interest. There's a lot of interest right now in one-shot learning. We're certainly not the only group to work on it. But just in case you haven't been following this particular little subfield of machine learning, the kind of thing we're interested in here is how can you look at, say, the first time you see a new kind of object, like a segue, and recognize other instances? Or in case you forgot what that was like, or in case you're not actively observing a kid who's doing that all the time with as they learn new words, think about something like this here, which unless you're an experienced rock climber, you probably haven't seen one of these things before, or unless you've seen me talk about this. This is called a cam. It's a piece of specialized protection equipment. And yet you still have no trouble looking at those objects on the bottom and seeing that some of them are likely to be cams, right? So how are you able to do that? Well, we still don't know. I can't say that we or anybody has a solution to this, in large part because the basic computer vision is still too difficult to actually look at those novel objects and get a rich 3D sense of the object for a new category. But what we've been doing is studying this in simple kinds of warm-up problems. So, for example, in the omniglot study that Brendan Lake did as part of his PhD thesis with Russell Kudinov, he tried to build a data set for studying this kind of rapid one-shot model building that was no more complex at the level of signals than MNIST, right? In fact, just like MNIST, it's basically a character recognition challenge that can be realized by looking at 28 by 28 pixels. Binary pixel arrays. But here, by taking characters in many of the world's alphabets, instead of just taking 10 classes, we have thousands. Notice that each one of those characters you can identify as a distinct concept from just one example, right? Each one of these things here looks to you as a thing, and it's different from the thing next to it. And you can do one-shot generalization. So again, if you haven't seen these demos before, I'll just illustrate. So take this object here. It's a character in an alphabet that's probably new to most of you, but you have no trouble looking down below and seeing another instance of it, right? So just clap when I get to another instance of that same character. Yeah, okay. So I was demonstrating a little bit of both intuitive physics and theory of mind there. You sort of predicted, we all knew it was coming, but then I defeated a little bit and we laughed at that little not very good joke. Okay, but that's not the point here. The point is your ability to see, even though the pixels of this, the correct answer aren't necessarily any closer to the pixels of this one than, say, that one. So how do you do this? Well, there's many ways to solve this, right? And at this point, a lot of people have been working on this problem. But the way we did it was, the way we approached it was to think of it as learning a very simple kind of program, or a kind of program induction, in particular the kind of action program or motor program used to draw a character. So think about, how would you draw this character? Just draw it in the air in front of you. Just try that. Right, so you probably did something like that, right? Okay. So this is, again, a kind of probabilistic program, we think, right? Your model of, you see the output, which is the pixel ink, and we're asking, what are the inputs to the control structure of your motor system, right? It's a causal model, because it's the causes of the output ink. It's compositional, because it has parts and subparts, or gestures, and higher-level motor routines. Okay, and at least in the model that we built, the so-called Bayesian program learning approach, the model learns to learn a number of parameters of these probabilistic programs from a held-out set of characters which are meant to capture like your sort of native alphabet. Okay, it's important here that when you think of this learning as a kind of probabilistic program inference, there's two levels of programs. The bottom level is what we call a token generator program. Here, each program captures one visual concept, one character, and each time you run it, you get a different instance of that character, realizing the variability, say, within those classes. Now, one-shot learning means seeing one execution of that program, one pattern of ink, and somehow making a guess at what's the program that generated it and could be run different times to generate others. And the way we think of that from a Bayesian point of view is to say, well, there's a higher level of programs. These are program-generating programs. They're also probabilistic, but the output of the higher-level program is one of these token generators. So the output of this program is a program, each time you run this prior program, if you like, it generates a different character. It just imagines a new character, maybe alphabet-specific or maybe just generic. And then the idea is to do a kind of a Bayesian inference to find the program which is, on the one hand, high probability under the program-generating program, but yet also explains the patterns of ink on the page. And then once you have that, you can do very, very good one-shot classification, but you can also do one-shot generation and imagination of new characters. So for example, here, this is a little visual Turing test where we can show you one character, and then we can ask you to draw another character. Just imagine another character. Don't copy, or another instance of the same character. Don't copy it, just make up another one. And here we asked 9 people to do that, and we compared it with our model. And we can ask you, as we asked other people, can you tell the difference? Anyone think they can tell the difference? If some of you have seen this before, do you remember? It's not easy. Think about it for a second. I'll show you the right answer. Think about which one is the machine. I'll show you the machine in a second. Okay. Here's the machine. Raise your hand if you got them all right. I bet a few of you did. Yeah, probably, 5 or 10% of you might have. Okay. Probably most of you got about 2 right, but that's just my guess. Okay, how about here? Can you tell? Here's the machine. One more. Can you tell? It's really pretty hard. Basically, you can't tell, and we have a lot of data to that effect. Okay, so this is just one small step towards how you might think about learning small programs from very little data. And what we and a number of others are trying to do at this point is to see where else can we go with this idea. So for example, can we learn other kinds of cultural symbol systems like spoken words or gestures? Can we learn other kinds of interesting cultural domains of objects like tools? Or for example, of course there's been a lot of interest in the AI community in learning video games for good reason, because those are models of learning new complex tasks and skills. Like, I think simple Atari games are actually a great instance of that. And while there's been a lot of progress, of course, everybody knows about it, whether it's from DeepMind or other groups, in learning to play Atari games with, say, deep reinforcement learning, it's still the case that the learning curves are nowhere close to humans. So here what you're seeing is just a few learning curves, the one on the bottom for this game Frostbite, which we've spent some time thinking about. Right? There's a basically very flat one on the bottom, which is the Deep Q network, which doesn't learn this game in even 1,000 hours. And then some more recent developments, which you can see here, are starting to learn this game to something like human-level performance in 100 hours, or there's recent developments that maybe can do it in 75 hours. Okay. Maybe even a little bit less than that. But humans can learn what they learn in just about 10 minutes, at least if you've ever played an Atari game before. Okay? We've got a lot of data on this. This is mostly work that Pedro Civitas is doing in our group with Sam Gershman and Zhao Luo and others. So I won't really talk about this, although we might talk about it a little bit at one of the workshops. But here we think that similar kinds of ideas of learning programs and reassembling components of programs can help to explain all these kinds of things here. Now, it's an open question, and I will really leave it open because it's a really hard one that's going to take a lot of work to even try to take a serious attack on. Whether this same kind of idea of learning programs can scale up from learning one concept or learning parts of a simple kind of Atari-like game engine to something like learning the entire game engine of your life. Like if we really think that what's going on in infant cognitive development over, say, that first year is somehow tuning a game engine to the physics and the graphics and maybe the people around you, okay, something like a game engine, then that's a really hard program learning problem. And I think if we're going to solve it, we're going to need to do something which we're sort of taking the vision of learning as programming your own mind to a much bigger scale. Inside our group, we have a sort of a slogan for this, which we call the child as hacker. You might have heard of the child as scientist, a popular metaphor, and more than a metaphor, to think about how children explore the world, form theories, their play is like experiments and so on. And we think to complement that, you need the idea that if your intuitive theories of the world are something like programs, then you need to be learning in all the ways that we hack on our code to make it more awesome. So I've just put up a bullet point list here of all these activities of programming, all the things we do in the course of a good day of hacking that make our code more awesome in one way or another. And they're all things that we think of as basically, I think there are corresponding activities in kids learning for all of these. And what we're going to need to make this vision real for AI systems that actually learn to be intelligent is algorithms, program learning programs that can automate all these kinds of activities, I think, or many of them. Now, I'll just show you one more example before handing it over to Vikash, which is just one instance. Again, there's many people actually. I mean, if you were at NIPS last year and you went to the program induction workshop, you saw a sample of some of the great work being done in the NIPS community. In our group, there's a few people, really brilliant students, trying to work on these very hard problems. I'll just mention a couple of things that have been presented in the NIPS community by Kevin Ellis, who's a PhD student at MIT who works with me, and also with Armando Solar-Lazama and some others. And he had a couple of papers that you might have seen at NIPS in the last year or two, where he's trying to, again, basically build systems that can do unsupervised program synthesis for probabilistic programs, for generative models, combining a range of tools, including tools that have been developed not in the machine learning community, but in the programming languages community, especially by people who've been trying for a while to get machines that synthesize some of their own code, like Armando's sketch system. And again, many people, or at least a number of people, are exploring the interface between machine learning techniques and, for example, these solver-based approaches. In Kevin's work, for example, he's used this to, say, learn a number of different aspects of language by writing down what's effectively a domain-specific language for the rules of phonology and morphology, the basic units of sound in language. This was from his NIPS paper the year before. Now he's been able to, by working with the linguist Tim O'Donnell and others, scale this up to take basically an intro phonology textbook, which has examples of sound systems in many of the world's languages, actually something like 50 or 60 different languages, including ones that most of us, again, have never heard of. And there's all these different rule systems. And right now, their system is able to get, I'd say, a solid B. If you don't allow partial credit, it gets a D. But if you do allow partial credit, it gets maybe a B+. So it can kind of learn 27 of the languages completely and good partial credit on most of the rest. And one last example of some work that Kevin has done together with Dan Ritchie, which I think is a nice way. There's no neural networks in this, but here's a nice way, again, the idea of using pattern recognition approaches as sophisticated versions of those in neural networks, combined with this idea of learning programs and really combining this with the Sketch programming languages toolkit. So here what Kevin and Ritchie were doing is to, say, solve this kind of problem. Take these hand-drawn diagrams, like some of them from some of our favorite machine learning models. We can handle both directed and undirected graphical models, and go from a sketch, literally a hand-drawn sketch, to some computer code which captures at a high level both the objects but also the abstract motifs like loops and conditionals. And the idea behind this is, again, to sort of break the problem into these two halves, to say, okay, well, there's the hand-drawn image, there's some kind of low-level graphics program with primitives like line, circle, arrow, and then there's the high-level code that has the abstractions, the loops and the conditionals. And a neural network, for example, can be used to do the first de-rendering stage, but then one of these program synthesizers can be used to find the highest probability and maybe shortest to execute, simplest code, which can be used to, as we're showing in these examples and others here, to be able to basically, you can see that what we're calling the trace set is just the low-level graphics code, then there's the more abstract code, which is significantly compressed. But not only does it compress, like any good compression, it generalizes. So here's examples of using the extracted code, just sort of running it forward with different parameter values, and you can see we can take these hand-drawn diagrams and kind of imagine idealized extrapolations of them to more objects. So again, these are small-scale examples, but hopefully what I've tried to show here and in the rest of the tutorial, and here I'll just sum up my part, is to say show a couple of ways in which human intelligence from very early ages goes beyond pattern recognition to model building, to try to take some insights from cognitive science about fundamental principles for how the mind builds models. So the idea of probabilistic inference over symbolic representations, the idea that those symbols give you compositional representations of causal processes that really put objects and their interactions at the center of things, and the ideas of learning at multiple levels of abstraction with, say, program learning programs. Okay. And hopefully you've given a sense of how tools from these several different communities are starting to help us solve these problems. And at this point, I'm just going to turn it over to Vikash to talk about how and can we actually scale these up to the real world. Again, in case you came in late, we're going to hold questions for about 10 or 15 minutes, a period we've reserved at the end. Now we have the AV excitement to...
Okay, so in the second half of the tutorial, I'm going to go through some background technology that's needed to take the ideas Josh talked about and implement them, and give a few examples of how using that technology it makes it actually feasible to implement these ideas and apply them to real-world examples. And I'm going to go in sort of the opposite order from Josh's tutorial. So we're going to, after going through a warm-up example to get a sense of what probabilistic programming is on a simple task involving curve fitting, I'm going to show how the same basic machinery can be scaled up to re-implement a recently developed AI system called the automatic statistician in just about 70 lines of probabilistic code. And what this system does is actually learns probabilistic programs that model time series data. And then I'm going to show how some of the same ideas can be used to implement scene understanding systems, including systems that infer goals from action using inverse planning, where I'll give code implementing a real video game planner and show how you can invert it to infer goals from action, and show examples and principles for inferring 3D structure from 2D images via kind of inverse graphics. And then I'll close with a summary of some future directions. So the field of probabilistic programming can be boiled down in terms of two core technical ideas. The first idea is that we can take probabilistic models and represent them using programs that make stochastic choices. And I'll show many examples of this over the course of the tutorial. But the key idea is that the model will be represented by a piece of executable code. And the variables, the variables in the model will correspond to stochastic choices made by that code. The second key idea in probabilistic programming is that operations on models, such as learning and inference, can be implemented as metaprograms. So these are metaprograms that take probabilistic programs representing models as input, and that, for example, find probable executions of those programs given constraints on their executions. And when you combine these two technical ideas, the result is a growing set of formalisms and software tools that help factorize the code that's needed for modeling from the code that's needed for inference. And the aim, or one of the aims of this effort, is to create tools which can do for a very broad class of probabilistic models this kind of factorization, analogously to how tools like TensorFlow and Torch do this for neural nets. So let's start with a simple curve fitting example, which I think has some of the essential features needed to understand the approach. So here are 4 data sets, each of which you can explain using some kind of, by fitting a curve, and in some cases making judgment calls about which of the data points are outliers. So the first data set might be well explained by a line. The second might be explained with a line with a couple of points as outliers. The third by maybe a quadratic or quartic, and the third maybe by a cubic polynomial with a single outlier. So we'd like to write a probabilistic program which can take data sets like these and get good answers essentially all of the time for a broad range of cases. So that's the problem we're going to try to solve just to get a sense of the machinery of probabilistic programming. So here's how we might write down a probabilistic model that could solve at least a part of this problem using the language of probabilistic graphical models, which will be familiar from many of the papers at NIPS. So we might define a model where the degree of some unknown polynomial is represented by a variable k, maybe chosen uniformly from first degree, second degree, third degree, and fourth degree polynomials. Then we might generate a parameter vector theta by generating draws from a Gaussian prior distribution over the coefficients of that polynomial. Of course, the dimensionality of that polynomial actually depends on the degree that was chosen. Then we could have random variables z sub I representing outlier assignments, so whether data zi is 1 if data point I is an outlier and 0 otherwise. And then those variables suffice to define a model, probabilistic model for y's, outputs y, given the x's, which just evaluates the polynomial at the input point. And the variance of the Gaussian probability distribution for yi depends on the value of z. So that's how z represents whether or not data point, z sub I represents whether or not data point I is an outlier. So this basic model is straightforward to represent using a program that makes stochastic choices. And here's the code. So I'm just going to walk through it. So there's some function which represents the overall model, which is going to depend on the input data, this set of x coordinates for all the data sets we're going to explain. Now what this code does is it defines the degree prior, here a uniform prior, so probability 0.25 is assigned to each of the 4 degrees. And the value of the degree variable is generated by making a stochastic choice from a categorical distribution where the probabilities come from that degree prior. And we're going to call that stochastic choice degree. And that degree term occurs over here in an execution trace of this program shown on the right, where it happened to return the value 1. The next thing the code's going to do is actually generate the parameter vector. And it's going to do that by iterating up until the appropriate degree, making stochastic choices to draw each coefficient theta from the appropriate prior. So in this case, degree is 1. There's 2. It's a first degree polynomial, so there's a constant term and a linear term. Those are shown in the trace over here with their randomly generated values on the right. And as one goes through this program, one can see how each stochastic choice made by the program shows up in the trace and corresponds to a latent variable in the probabilistic model we're going to then do inference in. So just reading a little bit farther, here in this loop, we're actually going to generate the y values for each input value x, depending on the degree. So depending on what the degree is, we're going to set the mean to be the appropriate dot product of the parameters and the basis functions. And then we're going to have a stochastic choice for whether or not data point I is an outlier. This corresponds to that z variable in the model shown earlier. Those show up in the trace over here. And then finally, we're going to generate the output value y from a Gaussian distribution, which has the mean we calculated up above and a variance that depends on whether or not this particular data point is an outlier. Here are 2 other traces of the same probabilistic program for the same input coordinates x. So in this trace, data points 1, 3, and 4 are being modeled as inliers, and data point 2 is an outlier. The curve is a quadratic. Sorry, the curve is a quadratic. And here we have a linear curve where none of the data points are outliers. So the key principle in probabilistic programming, again, is that a piece of code that's making stochastic choices induces a very broad, potentially, space of execution traces. And each distinct execution trace is a hypothesis in some probabilistic model. That's the basic representational machinery we're going to use for all of the examples in this tutorial. Now, one benefit of this representation for models is it becomes very easy to experiment with modifications. So the program that I wrote down has a whole bunch of arbitrary parameters, which we really had no particular reason to set at their given values. In particular, here the probability that a data point's an outlier is 0.1, or the inlier variance happens to be 1. Well, it's conceptually straightforward to treat those as latent variables as well. So give those appropriate priors, and add those as variables into some graphical model. But these kinds of small changes to a model conceptually can result in large changes to the software that implements inference in the model. So one of the main benefits of probabilistic programming in practice is it makes it much easier to experiment with many variations of the same basic model template. And we can see how this might be because it's maybe evident that it's just a small change to the program to make those hyperparameters also latent variables. So here's the old source code. And if we just add 3 lines where we assign inlier noise, outlier noise, and prob outlier to be stochastic choices from, let's say, 2 gamma distributions and a beta distribution, we now have a new version of the model which has a hyperparameter uncertainty. And this enhanced model actually behaves significantly differently in practice. So on the left here, I'm showing example data sets generated from the model with the arbitrary hyperparameters I chose at the beginning. And on the right, I'm showing samples where there's hyperparameter uncertainty represented. And we can see there's a broader range, including relatively noiseless data sets, which may be important for explaining some of the data sets I showed at the beginning. OK, so once we've represented a model, the next task is to perform inference. And in the field of probabilistic programming, there are many different approaches to inference that have been pursued. Here, I'm just going to try to give you a sense of some of their essential characteristics. So one interface to inference that's recurred in many languages is a query operation, which takes a probabilistic program. That program may have some input arguments. So in the example I showed before, those were the input coordinates. And then a set of observations. And what inference in this probabilistic program is going to produce is a trace of that probabilistic program along with a weight, which is some measure of compatibility between the execution trace produced and the observations. So I'm going to go, again, pretty carefully here just so that we have the building blocks we need to move more quickly later on in the tutorial. So just breaking that down in terms of mathematical notation, there's some distribution on execution traces, x, that's induced by executing the program. This you could think of as the prior distribution. So the probabilistic program somehow implies that prior distribution. Then there's another distribution, which is the distribution on traces you get when you take that prior distribution and you multiply it by a set of constraints that force various random choices in the trace to take on the values that are given by the observations. So this posterior distribution on executions is going to be the target or the goal of inference, producing samples from this distribution. So the way we're representing that on this slide is that there's some distribution that's produced by the query, Q, which is a distribution on traces x, given a program, the inputs, and some constraints. And our hope is that that approximates the posterior distribution on traces given the constraints. So this is a simple model of how inference in probabilistic program, of an interface to inference in probabilistic programs. So many different algorithmic approaches have been proposed in the field for implementing this basic interface, including importance sampling, simple Markov chain Monte Carlo schemes, more sophisticated schemes like Hamiltonian Monte Carlo, sequential Monte Carlo, particle Gibbs, mean field variational inference, approaches which I'll talk more about later, where Q is learned, at least in whole or in part, by generating training data and then using an appropriate machine learning technique, including deep learning. And some probabilistic languages, including Eyeball and Figaro and Infer.net, also use message passing algorithms to approximate the basic inference template I showed earlier. But all of this machinery is in service of helping users specify queries against models, typically emphasizing providing general purpose mechanisms that can apply to a pretty broad set of queries. So here's how one could use that interface to analyze data in the curve fitting context. So maybe I construct an empty trace to represent my observations, and I store the target value of 0 for the second y coordinate in that trace. And then I can run a query in my model where I have this list of x coordinates, where x is the x inputs are -3, 0, 2, and 3, and the observations here are just the single data point y at value 0. So here are two traces of the program that are compatible with that data point. They both are curves that go near that line. I can now add more observations to my target set or my constraint set. And when I do that and run queries, I now get queries that concentrate on lines that go near those data points. And of course, if I run a query without specifying any observations at all, that just corresponds to running the program forwards again. So sampling from the prior distribution on curves. So let's see how that interface, the kinds of results that a good implementation to that interface can produce on these examples. So if I just take a model that has no notion of outliers, actually the results we see look pretty wrong. And this is kind of what you might expect from a simple curve fitting approach. So in the second example, these two data points quite distort the slope of the curve, and the program actually thinks, it also calls in the hypothesis that maybe there's some sort of higher order curve, because that gets you a little bit closer to those outliers, especially that first outlier. If you add in outliers, the results get a bit better, but they're still a lot noisier than what we might expect by eye. But here, when we show inference results for the models where we have the outlier variables included and inference over the hyperparameters, we see a posterior on curves that closely matches what I think many of us have as our intuition. I mean, a very low noise curve in each of these three cases, these two data points very clearly outliers. Although in this case, the model is not so sure. Is this a line or is this a cubic polynomial? And I think maybe some of you are similarly at least a little bit uncertain. So this is the basic probabilistic programming setup. There are many probabilistic programming languages that are under active development today. I'm just going to briefly list a few of them here. So there's blog and problog, which were very early probabilistic languages that focused on integrating ideas from logic and probability. There are languages like Figaro and Infer.net, which are embedded in general-purpose programming languages, Scala and C# respectively, and they emphasized many advanced inference techniques, including message passing. There's a set of languages from the Bayesian statistics community, Stan, Libby, and PyMC. Languages like Church, WebPPL, and Anglican are all expressive modeling languages that try to provide automatic inference, chiefly but not exclusively by Monte Carlo. There's some new probabilistic languages, especially Edward, Pyro, and ProbTorch, which emphasize support for deep learning. And I'll say a little bit more about those again later. And then some other languages, including languages from my group, like Venture, which allows users to specify custom inference strategies adapted to the problem at hand, and languages like BaseDB, which provide integrated support for model discovery from sparse databases, so you don't have to write the probabilistic program yourself if you don't know how. And just one quick note on matching inference strategies and problems. So this simple curve fitting with outliers example is actually expressive enough to show the need for custom inference strategies. So here I'm showing results on a version of this problem where actually the curve is known to be linear. And these results, where we've got data now in green and inferred curves in blue, were obtained by using an inference strategy written here in the Venture language, which combines gradient-based search for the continuous parameters with Gibbs sampling for the discrete variables. This is a strategy that many probabilistic AI and machine learning researchers might think was reasonable for solving this particular problem. But in fact, if you apply other strategies that might be reasonable, very reasonable, or even optimal in other contexts, you can get pretty bad results even on this simple problem. So if you use a single-site Metropolis Hastings algorithm, even with quite a bit more runtime than the strategy I'm showing with gradient search, you get curves that actually don't correctly infer, that have a wildly distorted slope, and they're actually missing the correct outlier assignments. If you use Hamiltonian Monte Carlo, you do a little bit better, but you still get many of the outlier assignments wrong. And if you try to use a more custom inference strategy, there are many other custom inference strategies you can write. I won't give an exhaustive list here, but but the main point is that it's important to choose the right inference strategy for the problem at hand, and some probabilistic programming languages provide the linguistic support to let users do that. Okay, so now given that basic machinery, we can start talking about how do we scale it up to apply it to solve real-world problems. So the first problem I'm going to talk about is AI-assisted data analysis. And the instance of it we're going to describe, our group has explored a few, but the instance we're going to focus on is re-implementing a system called the automatic statistician. So the automatic statistician, which was work done by Dave Duveneau and James Lloyd and Roger Gross and a couple of other people in the NIPS community, including Josh and Zubin, can solve problems like the following. So here are two time series. One is atmospheric CO2 levels, the other is airline traffic volume. So I'd like you guys to just imagine and draw with your right hand, if you would, how you would extrapolate these two time series. So for atmospheric CO2 levels, can you just draw how you think the curve would go, say, out over in this region? Great. Right, so most of you did something like this. And what about for airline traffic volume? Right, so most people drew something which is linearly increasing, and then the amplitude of the fluctuations also increases. And in particular, none of you just went like this. Right, so a simple linear extrapolation misses a key pattern that's evident just by a glance at this data. And you know, everybody's basically right. So how can we build an AI system which can both replicate this basic intuitive capability we all have and put some quantitative error bars around it? So, you know, do the kind of data analysis that a statistician might do if asked to do forecasting for each of these time series. And, like all of us, choose both the structure, or identify the structural patterns, and make quantitative predictions with calibrated uncertainty. So the approach taken in the Automated Statistician project is an instance of one of the main themes Josh talked about, namely learning as a form of program induction. So this project developed a domain-specific language for time series data. And in this language, the basic elements were time series patterns like local variation, repeating or periodic structure, variation at multiple scales, linear trends. And these types of pattern primitives were implemented using Gaussian process kernels, which, when sampled from, produce time series realizations that have each of these types of patterns. And these basic elements or motifs were combined using a grammar for constructing composite kernels out of sums of kernels, products, and actually also change points. And it turns out that by forming simple combinations of these primitives, one can actually model a very broad class of time series. So if you just look at pairs of kernels, two linear kernels produce quadratic functions. You can produce functions that are periodic, but only locally, or periodic with some trend, like the examples we saw earlier. If you expand out the grammar just a little bit farther, you can find a very broad class of time series patterns that are spanned by this very simple domain-specific language. So if we look at atmospheric CO2 levels, we can decompose this time series in terms of a linear trend, a periodic overlay, and some random variation. And we can formalize that decomposition in terms of a particular expression in this little time series language. That's what I'm showing at the top here, this linear, where this can be read as a product of a linear and squared exponential kernel, and then a sum with a squared exponential, which is then taken as a product with a periodic and rational quadratic kernel. So we can see something analogous for airline traffic volume, where that time series can be decomposed into a linear trend, a periodic overlay, here with increasing amplitude, and then some local fluctuations. So if we want to build a system that can take the raw data and produce these sorts of decompositions, well, so the automatic statistician is a system that first does that analysis I just described and then produces a PDF report which documents in a combination of English and graphs how the time series decomposes. So here's how here's the basic idea for how we can re-implement this system using probabilistic programming. And this is work done chiefly by my postdoc Ulrich Schechtel, my grad student Faraz Saad, Alexei Rodel, an engineer in my group who's now at Google, So the basic idea is we're going to take these little time series expressions and treat them as data structures representing a probabilistic program. So here I'm showing a data structure representing a time series with a change point that's located at 4.5, and then a product of a linear and white noise kernel. And then on the right side of the change point, there's another white noise kernel. Over here, I'm actually showing 3 time series realizations. So you can see that at 4.5, to the right it's just noise. To the left there's this linear trend with noise added. That corresponds to the structure on the left. And the link between these two is that this data structure can be thought of as a probabilistic program that actually implements a Gaussian process model. So the problem of going from data to these structures can be thought of as the problem of learning very simple programs in a domain-specific language. Now, the way we write down a system that can do this type of learning is to write a metaprogram, a probabilistic program that generates representations of probabilistic code. So in some sense, this is just a slightly more complex version of the curve-fitting example I showed earlier, but from another perspective, it's qualitatively much, much more expressive. So here's code, again in Venture, that implements a grammar-based prior over time series programs. Although I won't go into the details of the code, roughly what this code does is it has subroutines for generating hyperparameters, choosing the basic elements or the primitive kernel types, choosing composition rules, and then recursively generating probabilistic program source code by flipping coins to decide what structural choices to make. And then once those choices are made, populating them with the appropriate continuous parameters. So this is code which, if you run it many times, generates time series programs. And then the inference task involves taking some data and inferring probable executions of this time series generating metaprogram from data, or learning probabilistic programs that describe the data. So the way that code looks, this is sort of the main entry point, is there's an expression which assumes there's some unknown source code that's obtained by generating a random program that's turned into a Gaussian process model, some executable, where you load the x's and y's from some data file, and then ask the probabilistic programming system to observe or constrain that running that executable on some inputs gives you the outputs that you loaded. And then you specify a custom inference strategy, where the particular inference strategy we use is one that does block gradient descent on all the continuous hyperparameters together for 100 steps, and then does 100 steps of a simple Markov chain Monte Carlo move to repropose one individual structural random choice at a time. And then that whole thing repeats for some number of iterations, and then the trace at the end is the time series model that'll be used for, let's say, whatever extrapolation or interpolation task you're interested in solving. And here are some example results. So here's the airline passenger time series I showed earlier, where you can see that so now here the predictive curves are shown in green, the real data is shown in black, and then these red data points are data points that are held out, just so we can get a sense of the accuracy of the extrapolation. And then on the bottom, I'm showing solar irradiance data where there's an interpolation task. So, we're trying to fill in the time series in the red regions. Here, the red region, and this red data seems to be periodic, whereas this data seems to be constant. So we need to form qualitatively different kinds of prediction in those two different regimes. And in both these cases, this system that learns probabilistic programs is able to do a pretty reasonable job of capturing the qualitative structure and then making quantitatively reasonable predictions. So just digging a little bit deeper into the airline example, we can take a look at how the system moves from the prior to the posterior. So here are 3 sampled executions from the prior on programs for the airline example. So these, we wouldn't expect to match the data on the bottom. They're just sampled programs drawn from the prior. So this one is essentially just white noise and some linear trend. This one has a change point. None of them look like the real data. But after doing inference, using the inference strategy I've shown, we can see 3 different sampled traces, where each trace represents a probabilistic program now, but drawn from the posterior. And now we can see that the predictions in all 3 cases match the data pretty reasonably, although there's some variation. And actually, we can see that there's a pretty broad posterior on different structures. So it's not like this data uniquely pins down a single program. We might expect there to be posterior uncertainty in this type of complex learning task. I should say, it's still clear that from the standpoint of learning programs, I think this is interesting progress, but it's also clearly very basic. These programs are simple expressions, maybe just a few levels deep, and we're a long way from scaling this approach to learn, even small components of game engines, let alone the whole game engine. But I think it's striking to see that we can actually use probabilistic programming to implement this approach in what turns out to be about 50 times less code than is required for an implementation using traditional programming languages. And just to get a sense of it, the whole probabilistic program synthesis program fits in about a page. It's 69 lines. That's resting on about 2,000 lines of libraries for the Gaussian process models, and the entire probabilistic programming implementation is another 2,000 lines. So it's really only 70 lines that were written for this application. And that's compared to about 4,000 in the original paper on model discovery for the automated statistician. So that hopefully gives a sense of how this simple idea of representing models as programs can help us start to implement ideas like learning programs from data and begin to apply them to real-world problems without kind of just drowning in the engineering complexity of the task. Okay, so now let's move from learning programs to examples of scene understanding. So first, I'm going to talk about inferring goals from action via inverse planning. And this is just meant to give a taste of how a realistic video game component can be used inside a probabilistic programming system. So the setup, which Josh mentioned in his part of the tutorial, involves inferring goals from actions via inverse planning. So we want to define probabilistic models which use planning algorithms to show how an agent's beliefs and goals contribute to its actions or inform its actions, and then work backwards. So in the setting we're going to work in is where the belief corresponds to the map of a scene, the goal is some destination in the scene the agent's trying to get to, and the action is the motion taken by an agent. And so we're going to want to solve problems like working backwards from observation of the motion and the beliefs, so what the map is, to inferences about the goals of the agent. So here's just a simple example so you get a sense of what inferences this probabilistic program can make. So here I'm showing a little world, and this symbol here is the drone's location, and I'm just going to show you the path the drone took. So a sequence of steps this drone took while flying around. And I want you to raise your hand when you think you know whether or not the drone is trying to go inside this room here. Okay, so by the end, some people started to think that seemed maybe plausible. So let me just show some inferences. So here now I'm showing inferred destinations, the samples from the inferences about destination from a probabilistic program that I'll describe in more detail in a moment. And now let's change the scene to put a door at the bottom and show the same type of data. So now, raise your hand if you think that the drone is definitely not going inside the room. All right, so people tend to be much more confident as soon as the drone passes this corner, because this would be a strange way to get inside the room. It seems inefficient somehow. Okay, so the probabilistic program makes essentially the same inferences. So how do we write a probabilistic program that can do that? Well, the basic building block we're going to use is a path planning algorithm, which is going to be built out of a rapidly exploring random tree followed by trajectory optimization. And I should say all of this is work that was done principally by Marco Cusimano-Towner, my grad student, and Alexei Radul and David Wingate. So the rapidly exploring random tree, here I'm showing the pseudocode for this very standard path planning algorithm, works by building a stochastic tree that roughly spans the space, and then planning a path from start to goal following just links that are contained within the tree. And then trajectory optimization involves just running some stochastic search steps on that path to move off of the rapidly exploring random tree to just get something that looks a little bit more optimal. So that algorithm is going to be our generative model for planning. And we're going to represent that using code. That's, in some sense, much like the the curve fitting example I showed you earlier. And it's going to define a space of execution traces. But these execution traces contain thousands of random choices for every realization of this model. So it's a much more complicated scenario. And if we were to represent this model as a graphical model, it would be quite difficult to work with. There's all the stochastic choices made by the rapidly exploring random tree algorithm, all the stochastic choices made by the path refinement algorithm. Then there's the actual measurement and motion model. So we're going to add some observation noise to this model to allow us to have some slack or some tolerance in case the agent doesn't exactly follow the predicted path. And all of that leads to a very complicated set of state machines that are all interacting. Okay. But once we've represented this in a probabilistic programming system, it's easy to use general-purpose mechanisms for Monte Carlo to get inference results like what I showed you earlier. It's also possible to change the query just slightly to solve problems like inferring beliefs from observations of motion and goals. So let's say we wanted to solve the problem of figuring out, does the agent believe that there's a door or not in the top of the room? So we can start from a version of the program which just has unknown start and destination, and add to it a stochastic choice for a variable representing whether or not there's a door. That's a small change to the problem, and that lets us solve problems interpret data like this, where we can get inferences of whether or not the agent probably thinks there's a door from the implicit evidence in their motion. And we can see in this case that as the agent goes down this path, the system becomes fairly confident, knowing that it's trying to get in the room, that it doesn't think there's a door at the top. But in fact, we can also make the goal unknown and perform joint inference on beliefs and goals. And in this case, the agent is the inference engine is much less confident until it sees a lot more implicit data, like that the agent is kind of tracking in this direction. Because it's not sure where the goal is. There are other explanations, like maybe it's just going here because that's its goal directly. Okay. So that's an example that sort of helps us bridge the gap to show how you can write probabilistic programs that that can infer goals from action using inverse planning. But let's go one step closer to real scene understanding and look at inferring 3D scene structure from 2D images. So the basic approach we're going to take is called generative probabilistic graphics programming. This is a line of research which we've been pursuing for about 4 or 5 years, which can be thought of schematically as formulating the problem of computer vision as sort of a direct Bayesian inverse to problems of computer graphics. So graphics software lets us go from structured descriptions of scenes to rendered images, for example, by simulating the processes of image formation. And that leads to a view of those same graphics algorithms as the building blocks for generative models, where if we could only invert them to infer the scene inputs given images, we could get good solutions to a broad class of vision problems. So here's an example of an implementation of this proposal that was done by Tejas Kulkarni and Pushmeet Kohli, now at DeepMind, Josh and myself a few years ago. So the problem that the probabilistic program is solving is taking observed images, shown in this column here, and answering the question, what would the underlying face behind this image look like if we rotated it or lit it differently? So imagine what this face looks like from some different viewpoint with different lighting. And to do that, the probabilistic program is going to infer a 3D model of the face, and then we can sort of check the validity of that model by looking at how it reconstructs the data. And then we can apply graphics transformations to that model to infer what the face would look like from a different viewpoint or with different illumination. So here's a schematic for the probabilistic model and the probabilistic program fragments associated with it. So there's a stochastic scene generator, which is a little block of stochastic code that makes choices to drive an off-the-shelf graphics model for faces, which involves generating a random mesh, texture, and camera and lighting position. And this is, call it roughly a 100-dimensional hypothesis space. If we render a randomly generated face, we might get a face image like this. Or if we just ran this little probabilistic program fragment many, many times, we would get many different random faces. But the inference task involves taking real image data, somehow comparing it to the approximate rendering, and then working backwards. And we're going to work backwards using a combination of two different types of inference techniques. One, custom inference strategies, like I showed earlier from Venture, specifically where the user can specify how to combine elliptical slice sampling, gradient search, and other Monte Carlo techniques, with learned bottom-up proposals, where a way to do fast bottom-up inference is learned by using training data that comes from running the graphics engine forward to generate fantasy data. So the face example I just showed takes about a page of code in picture. And here's what it looks like when run on real data. So you can see that on the left here I'm showing the input data, and on the right I'm showing the sequence of reconstructions that the system moves through as it's performing inference. And you can see that initially the inference engine is making big changes to the scene, which then becomes smaller over time as it's fine-tuning details to get a good match. And the big changes are coming from the bottom-up proposals, while the small changes are coming from the gradient search and elliptical slice sampling. But the same basic proposal can be implemented for many different vision problems. So, for example, here's a use case. We'll see if we can show the movie for inferring a 3D model of a human body from outdoor images. So we're using an off-the-shelf graphics model, about 20 dimensions, and we're explaining this input image. And this is the reconstruction of the inferred pose, analogous to the reconstruction of the face from the previous example. And this basic approach applies to just using an off-the-shelf graphics model driven by random inputs, applies to a broad class of test images, including test images with people sitting in chairs where they're partially occluded. And although I won't go into the details in this tutorial, the quantitative results for this reconstruction compare favorably to state-of-the-art baselines from computer vision in terms of measures of error for reconstructing specific joints within the pose. Also, we can see how to scale up this basic approach by adding another layer that's analogous to the metaprogramming layer Josh talked about earlier. So what if we wanted to model an open category of objects, like all radially symmetric objects, like lamps or wine bottles or cups? So this paper also shows how to model those by generating a curve, essentially from one of the curve fitting models I showed earlier, but treating that as the edge that's then rotated in a computer graphics operation called lathing to generate a mesh for the contours of an object, which is then used with the same rendering machinery from the other examples. And inference in that model explores hypotheses that initially look like sort of strange radially symmetric objects, but then converge over time to reasonable interpretations of the 3D structure for these input images. And this approach applies to a broad category of objects. So this can be thought of as a kind of combination of the program learning material I showed earlier with this graphics domain, where the program we're learning describes the parametric curve for the contour of an object. Similar models have also been used to solve problems that are more relevant for robotics, although this work is very much in the early stages. But here's an example of inferring a 3D model of a roadway, where I'm showing the inferences from the probabilistic program on the left and inferences from a bottom-up computer vision pipeline on the right. And the key point here is that because inference in this probabilistic program produces coherent scenes along with a measure of uncertainty that's implicit in taking many samples, it can be used to solve, it's appealing from the standpoint of building a front end to a perception system. So over here, because it can produce uncertainty over the scene interpretation and kind of report when its modeling assumptions are not very well satisfied. So here I'm showing an example frame where there's a road that crosses the main road that the car is driving on. And this frame violates the basic assumptions in the simple generative model that was used for this problem, where there's a single lane. But that violation is actually evident in a high posterior inference for effectively the inlier variance and a broad posterior uncertainty over the scene geometry. Whereas for frames that better fit the data, the posterior uncertainty is much lower. So this kind of ability to report coherent uncertainty over aspects of a scene is an appealing engineering consequence of this inverse graphics and probabilistic programming approach to scene understanding. So we say a little bit about how we learn fast bottom-up proposals and talk about work that's been done by some other researchers in the field, including some excellent recent work by Frank. So in this picture example, one of the techniques we used was to learn bottom-up proposals by taking the probabilistic program, generating many fantasy traces, extracting target variables, so specific aspects of the pose, and generated image data, and then using those to try to learn a model that would let us work backwards somehow directly or in one shot to infer probable hypotheses given data. And in the case of the 3D pose example, here I'm showing a collection of those fantasy execution traces overlaid with the true latent poses associated with each trace. Now in the picture paper, we just did a very simple hashing-based learning approach, really hashing followed by kernel density estimation to learn bottom-up proposals. So a classic, simple machine learning technique. And it turns out that that's actually useful in practice. So here's an input image, and here are the 3 best bottom-up proposals for that input image. So these are the centers of the center locations for bumps in the kernel density estimate for the learned model that inverts that graphics pipeline shown earlier. And here we're showing the log likelihood versus amount of computation. You can see that the blue curve, where these data-driven proposals are learned, ascends faster than the curve where simple slice sampling and gradient search are used on their own. Now, if we use a slightly more complicated bottom-up model, for example, here in this face example, we're using a convolutional neural net that's trained to predict aspects of the face scene and the pose and the lighting. The results are much more striking. So this is work done by Ilker Yildirim and colleagues, where very rapidly the inference engine gets to an interpretation of the input phase that's better than what's found after many, many passes of MCMC inference. This theme, using neural nets to accelerate inference in probabilistic programs, has been pursued by several researchers, especially recently, so I'm just going to highlight a couple of examples. There's work by Ritchie and Noah Goodman, Pat Hanrahan on neurally guided sequential Monte Carlo, and this technique turns out to be featured very prominently in the Pyro probabilistic programming system recently released by Uber. There's some work on inference compilation by Lee, Baden, and Frank Wood, which I'll go into in a moment. And then there's a version of this idea for inference within, or for a subset of variables embedded within a larger probabilistic program that was done by Marco Cusumano-Towner, one of my students. So let's just take a look at the inference compilation approach from Frank's group in a little more detail. So the problem setting that they applied it to was a scaled-up version of this basic CAPTCHA example from generative probabilistic graphics programming work done earlier. So the CAPTCHA breaking example involves going from input images, here shown on the left, to a reading of what are the characters in that input image and the ability to denoise the image, so to render it without distortion. And those outputs of the final inferences are shown on the right. So the approach that was taken in Frank's inference compilation work was to use the probabilistic program as a source of cheap, fast training data for an appropriate neural net architecture, which could then make a sequence of bottom-up proposals to solve the problem. And in the case of the scaled-up CAPTCHA problem they solved, so here I'm showing a figure from their paper which describes the generative model for Facebook-style CAPTCHAs. And there's a natural sequential structure to generating the CAPTCHA, which involves putting the letters down in sequence and then adding various notions of noise. And there's essentially an LSTM that's used to structure the bottom-up proposal. So the sequential structure of the generative model is paired with a sequential structure for the fast bottom-up inference algorithm. So this is a more sophisticated example of how you can use neural network learning to accelerate inference in probabilistic programs. And using techniques from other languages I've talked about earlier, this can be combined with a wide variety of custom inference strategies. Okay. So what we've seen in this half of the tutorial is what probabilistic programming is. This basic idea of representing models using code that makes stochastic choices, and then implementing metaprograms that explore the spaces of execution traces of code to do operations of inference and learning. We've seen an application to re-implementing the automatic statistician to provide a kind of AI-assisted data analysis And we implemented that as a probabilistic program that learns probabilistic programs from data. And we saw that it was possible to do that using far fewer lines of code than is possible if the inference algorithm is implemented directly. And we saw a couple of examples of simple forms of scene understanding using probabilistic programming languages, where the generative models were built using the building blocks of video game simulation engines, and a range of inference techniques appropriate to each task were chosen to do the inversion. So I hope this is starting to give a sense of how the basic kind of AI program that Josh mentioned in his half of the tutorial could be implemented if we can make probabilistic programming languages that are sufficiently usable, testable, debuggable, scalable, fast, and mature, and learn how to write programs in those languages. So I think there's a big project ahead, but some of the key elements of a solution may be emerging. So let me just say a little bit more about some specific future directions of research along these lines. So I think there are three themes that are central to the thinking of many researchers in probabilistic programming who are interested in artificial intelligence. And the main one, or a main one, is to develop a deeper integration of probabilistic programs in deep learning. And that deeper integration ought to involve learning for at least three different subproblems. One of them is learning to do real-time inference, which I've shown a few examples of so far. But a second is learning non-parametric models for aspects of the problem where driving, let's say, an off-the-shelf simulator with random input is unlikely to be adequate. And a third is using learning to compare explicit simulators with real data. So let me just dive into that first one for a moment. So at one level, the idea of using neural networks to invert graphics models, let's say, is intuitively appealing, but it's, at least at this point, not really clear how to implement it in detail. So here are some questions that still need to be answered for understanding how to execute this integration. One of them is where and when in generative model and in inference to use a simulation engine as opposed to a neural net. What are the strengths and weaknesses of each approach in context? The second is what training objectives or targets to use for neural networks, and what training protocols more generally. A third is what intermediate representation should be used, both maybe as the target outputs of the neural net, so how should the neural net learning be guided? And actually what training data should be used. And there's a key, one key idea which is appealing to many of the researchers in this area, which is to exploit conditional independence, or to integrate some of the basic insights about the most important features of causal modeling from Judea-Pearl with ideas from Jeff Hinton. So somehow might it be possible to take advantage of conditional independence in the simulator that's evident in an explicit model of the generative process to provide structured answers to many of these questions. What should the neural nets be trained to do, and how should they be trained? And maybe even, what should their architecture be? So, for example, in this kind of, if we look at the problem of inferring 3D models for indoor scenes, just looking at the coarse, say, shape of a room and the location of boxes within it, maybe there's scene structure, which includes many different objects. But then the relationship between those objects and the real fractions of image data they're associated with is actually quite indirect. But in computer graphics and in computer vision, there are mid-level representations like intrinsic images or shading maps, various kinds of image-shaped buffers or 2.5D sketches that naturally arise both in graphics and in vision as an intermediating layer in between, say, objects rendered without any notion of appearance and the raw image data itself. So one potentially appealing idea is to use representations like this, which are already part of the forward graphics pipeline, and in particular the conditional independencies that knowledge of those representations creates to structure the use of neural nets for inference. And here's just a preview of one example that's work done principally by Jiajun Wu, one of Josh's students, that's being presented in the main conference, where the idea is to learn how to go from images to 3D shapes by moving through an intermediate representation, which is very similar to a 2.5D sketch or a map of depth with a surface normal. And this basic proposal is implemented in the context of an inference network which is trained from completely self-generated data. So the idea that by learning to infer 3D shape using a forward graphics engine to define the model, but explicitly learning to invert in terms of first inverting a 2.5D sketch and then inverting 3D shape given knowledge of that 2.5D sketch, it becomes possible to solve this problem in real time and in a very nice way train an inference network that provides a suitable inference engine for this task. And this basic approach gives pretty appealing results on hard real-world data sets. So here are some examples of the approach is called MARNet, and this shows examples of the inferred 3D shapes on a range of real-world images, in this case of chairs, which have widely varying geometry. Of course, understanding how to take this specific instance and implement it as part of an inference compilation strategy for a general-purpose probabilistic programming language is very much an open problem. But I think partly by carrying out deeper integrations of probabilistic programs with deep learning, we may be led to optimize probabilistic programming platforms, at least for scene understanding. The last line of research that I want to discuss before the question period is I just want to mention, to call back Josh's comment about the different timescales on which intelligence unfolds, from perception, which might take milliseconds to a second, through thinking, which might take a second to a minute, or learning, which might take minutes or hours or up to a day, and then longer timescales of development and cultural evolution. So some of the last scene understanding examples I showed were really about the interaction of probabilistic programs and neural nets for perception. But the earlier examples I showed, I think, got a little bit closer to some of the simplest aspects of thinking. And so I think it's appropriate to ask what technology might be needed to really help scale this approach to AI engineering and reverse engineering farther up the spectrum from perception to thinking. And I think there are two key directions that seem salient to us right now. The first is meta-languages for modeling and inference. So right now, all of these different probabilistic programming languages I've described can't really implement approaches from one another or interoperate, but we might like to develop meta-languages which allow people to compose probabilistic programming strategies and inference strategies that are currently require separate languages within a common framework, both to scale up the expressiveness and flexibility of the models and the inference strategies. And a second key piece of technology is to make the Monte Carlo techniques, which may be central to some of the inference problems in thinking, really, really fast. And if we contrast Monte Carlo inference with, gradient optimization and, related computational kernels like matrix vector multiplication and linear algebra, we can see that, the performance of, let's say, MATLAB is resting on decades of very hard performance engineering work led principally by industry to make those computations fast, both in software and hardware. And this raises the natural question, if we want to scale up AI to handle more problems that are more like thought, maybe we need to develop fast runtimes for Monte Carlo inference that can be targeted by probabilistic programming languages. So one way to think about it is what would be the analog of the basic linear algebra subroutines, but for Monte Carlo inference? Good. That's it. Thank you very much. It's time for questions. And for questions, just please come up to either of the two microphones, and we'll call on you.
In the first part, in the automatic statistician, at the end you show a plot of the expected outcome and the uncertainty. And I was wondering, do you take into account in that plot the uncertainty over the generative model?
Yeah, the uncertainty over structures.
Yes.
Yeah, that's right. It's a great question. So we found that the prediction accuracy is improved at least a little bit by averaging over multiple model structures. Although I think the most important application of uncertainty over structure is actually for querying the latent structures. So let's say I wanted to answer the question, is a given time series probably periodic? Or does it have a linear rise, let's say, if it's a macroeconomic data set, right around 2008 when the markets went crazy? So I wanted to do a search operation on time series. For those types of queries, you really need posterior uncertainty over the latent question, the latent structures. For prediction, I think there is a quantitative improvement, but at least so far, it's not clear how essential it is.
Thank you.
So a question about this slide, the third one, when you say both meta-language, well, the same question applies to both. Are you aware of any specific work in either of those two directions?
You can see, so BaseDB, for example, a probabilistic programming system I didn't mention in this talk, provides a meta-language for building models using model discovery and composing models from different probabilistic programming languages. That's one partial answer to this problem. And then both the metaprob language and the gen language, which are two still unpublished languages but projects in my group, are directly aimed at addressing these questions. There have also been some early conversations with some of the big tech companies about developing runtime libraries for Monte Carlo that I'm happy to talk about.
Thank you.
So this is a question I think you could both provide input on. You talked a little bit at the end about making Monte Carlo inference faster. So if we're to believe Josh, humans are doing something like that. And clearly we do not have, well, I guess maybe a neuron's linear algebra optimized, but we don't have that much computing power up here. So do you think that we can learn anything about designing inference algorithms by looking at the way humans are thinking or trying to solve these problems?
Why don't you go first?
Sure, yeah. If you were to believe me, I wasn't arguing that humans are doing Monte Carlo inference. I was arguing humans are doing something approximating inference in probabilistic programs. One way to do it might be various kinds of Monte Carlo, or another way might be the right kinds of, say, neural networks, at least in the context of, say, certain kinds of image-based scene understanding, or maybe certain kinds of dynamic tracking problems. You know, the motifs that you saw in deep convnets or LSTMs might be good ways to approximate inference. In other contexts, like certain kinds of learning problems, maybe not. Again, as Vikash said in the future directions, I think it's very exciting to explore the full ways that all these inference approaches can integrate. But having said that, I think if you look at what computational cognitive scientists have done over the last few years, they've been exploring using behavioral methods as well as a range of these models to try to actually dig into what seem to be the kinds of inference algorithms that people use. I can give one example that was kind of surprising in retrospect, or surprising at the time as we and others were discovering it, but then makes a lot of sense in retrospect, right? Which is, it often seems as if when you look across the kind of experiments that I showed you, right, where I was comparing the average data of a group of people across multiple trials, each person made each judgment a bunch of times, and we took the mean, and then we compared that with the mean of one of our approximate Bayesian inference systems, you get a nice correlation. But in any one trial, it often looks as if people, especially if they have to make a discrete response, like will it fall or won't it? Or is this a cam or isn't it? Or is this thing? It often seems as if people are responding at each moment with, say, one posterior sample. We wrote a paper, this was Ed Vool and Noah Goodman and Tom Griffiths, and I wrote a paper called One and Done, which was looking across a number of different settings, both in perception and cognition, where it seemed as if people were choosing one posterior sample. In some more recent work, I should say, the point of that paper was also to explain why that might be a good idea, that there's a lot of problems in Bayesian inference that, at least for the purpose of a brain, and probably a robot, although it's very different from the goals of a Bayesian statistician, in a sense, one sample is basically the optimal cost-benefit trade-off of the cost of inference and the value of inference. You could wait longer and get more samples, right, or use or parallelize, but there's a strongly diminishing returns, at least for many kinds of decision problems. The first sample tells you a lot more than zero samples. And not only is there a strong diminishing returns, but the opportunity cost, or the fact that the world might change, suggests often just take one or a small number of samples and then move on. In some more recent work by Falk Leader, which some of you might have seen at NIPS, he's a PhD student with Tom Griffiths at Berkeley and others there. They've shown that sometimes the optimal thing isn't just one sample, but actually less than one sample. Basically, if you run like an MCMC algorithm but don't burn in fully, right? Sometimes with a good initialization and just a little bit of iteration, the bias variance trade-off still favors that sort of approach. Again, because of speed accuracy trade-offs, basically. So, that combined with some of the neural net inference, or the idea that a deep neural network might be like, an importance sampler, or somehow giving you one approximate sample, or even, a biased but still good enough sample very, very quickly. That's, I think, one place where in cognitive science and maybe computational neuroscience, we're starting to see some inspiration.
And I just want to add to that. I think it's a really important question. So 3 quick comments there. The first one is sort of layering on what Josh said. I think at both both from our study in psychology and in neuroscience, there's evidence to think that a key difference between Monte Carlo in this sense here and Monte Carlo methods as they were first developed, let's say in computational physics, is that the methods are being used at very low precision. Very low precision because the model parameters they're being applied to are themselves unknown, because the decision problems being solved only need rough answers, because only a couple samples are needed, because the samplers don't need to really burn in that far. So for all those reasons, the precision requirements might be very low. And that is both maybe an interesting match psychologically and with the engineering requirements, and brings us a little bit closer to understanding how a brain-like computing machine might be able to implement these techniques. So if you think about Monte Carlo as approximating high-dimensional integrals, okay, this maybe seems like a strange strategy to use for engineering intelligence. But if instead you ask how could you implement fast, massively parallel circuits for very low precision sampling that use very low precision internally, that's maybe getting a little bit closer. And actually Eric Jonas and I did some work on intentionally stochastic digital hardware, which is attempting to explore one such hardware proposal for implementing Monte Carlo custom computing machinery for Monte Carlo techniques based on those basic ideas. It's a great question.
Thank you.
Hi. I have a question about the primitives. So reverse engineering, or kind of the inference to be able to find these intermediate or underlying representations is really exciting. But what they require is that you have the framework and the primitives ahead of time, right? And I was wondering what you can do to talk a little bit about what are good scalable sources for getting some of these primitives, and kind of what you've come across and what you found.
Can I just ask? I mean, be more specific. Like, which kind of primitives are you talking about?
So, for example, on the time scale example, you would need these primitives like recognition of some periodic oscillation, some basic linear trend, right? Those are all things that we know we can program in, but in a broader set of domains, what are some scalable ways of getting those primitives?
I mean, I don't know if you want to weigh in on that. I think you're asking a big and deep and hard question that is not only a question for this approach, but for any engineering approach to intelligence, right? I mean, you could ask the same question in deep neural networks, for example. Yeah. When somebody came up with the idea of LSTMs, or when somebody came up with the idea of skip connections, that was a really good idea. How'd you come up with that, right? And what makes any toolkit for either modeling the world or building intelligent systems powerful is when you start to see that that people are putting more and more tools together and then having languages for composing them. So I think that in that one example, that language of compositional Gaussian process kernels is one instance of that, and we have others. I think I mean, again, you could ask, looking in a big sweep way, you could say, well, what I was arguing on one of my last slides about the idea of learning as programming, all the different ways we hack on our code, the idea that if we can scale up learning as some kind of assembling not only individual programs but libraries of programs, that's one of the big things we do as programmers, right? Is we come up with libraries that provide useful primitives for other things, often by recombining elements from somebody else's library. If you look at how human learning works in an individual's lifetime, or if you look at, say, cultural evolution, that's a lot of what you start to see. You start to see that kind of library assembly and library learning. We are far from being able to automate that with the kind of tools that we have right here, but that doesn't mean that we don't see ultimately some kind of scaling path along that route. And I think if you look especially what the people are doing in program induction and program synthesis and all the places where machine learning meets up with programming languages. I think that's our best hope for trying to address the big problems you're talking about.
I'll make one other comment, which is really from an engineering as opposed to an AI perspective, right? So I think the AI version of that problem is very hard and interesting, and maybe we can talk about that afterwards some more. But just from the standpoint of engineering applications like AI-assisted data analysis or certain types of machine-assisted scene understanding, there, I think that actually the functional requirements of an application and our natural language descriptions of those functional requirements and the formal languages that have been developed in other fields are all very good guides. Okay. Right? So, for example, if I wanted to do AI-assisted data analysis, it's not just an accident that periodic and linear structures or local variations are what we chose. Those both correspond to tools that were available from statistics, but also types of questions that people want to know the answers to in specific linguistic terms. Right. Okay. And I think that's actually
yeah. There's a wealth of existing primitives that we can rely on at least initially.
And in some cases, even if we could learn those primitives, we would still then need to learn a mapping between the thing we learned and the thing we already know the word for to actually build the system that works for a given application. But again, that's only from an engineering standpoint. I certainly don't mean to dismiss the very hard problem of how would you learn, the primitives themselves, in a fully unsupervised way. Although there, I think the question of timescales is also important to keep in mind. What timescale are we trying to model the learning at? Right. Okay.
Thank you.
Hi. I'd actually like to expand on previous listeners' question on the primitives, but rather not the general AI epistemological question of where do we get them from, or maybe that slide Vikash talked about learning a human pose from off-the-shelf graphical models when you have 20 dimensions, I guess. So doesn't it kind of restrict you to the scene understanding of a specific kind, namely of the human pose, which can be represented by these 20 dimensions? So do you see that as a challenge, as an issue? How do you propose to combat this?
So that was one example of, here's one scene understanding problem, which is understanding bodies in space, right? Now, that's not a full scene understanding system, but what that represents is a module that has a representation in terms of a probabilistic program for an important class of objects in our actual lives, and then some inference algorithms which are specialized to doing that inference very fast. Now, you might say, well, do I really want to have a module like that? It turns out that every one of your brains has one. It's called the extrastriate body area. Okay? And there's also a face area. And there's areas in the superior temporal sulcus that we think implement something like generative models of faces. Now, I don't think, again, I'm citing my colleagues in cognitive neuroscience who've helped to discover and are starting to map out the representations in these parts of the brain. But it's interesting that the visual parts of the brain, especially higher level parts of the brain, seem to consist of a couple, or actually some number of different modules which do the kinds of things we're talking about here. If you go to the workshop on Saturday on disentangled representations, Doris Sau, for example, I think is going to be talking about some of the latest work mapping out these kinds of basically specific modules and some general purpose object ones that might look like some of the things Vikash talked about here too, in primate brains, in non-human primates, and monkeys, where you can really study not just the large-scale brain areas, but some of the detailed pathways of representation. And it's a really exciting place where the kinds of ideas we're talking about here are starting to meet up with human and non-human neuroscience. At the same time, I don't think, again, scene understanding is not just those modules, and something that we still don't understand on the neuroscience side, and that we're still trying to do here on the engineering side, right, is understand, okay, well, how does that all come together into a scene understanding system that, again, recognizes, detects the objects, but also integrates with physics and prediction, is multimodal, integrates across vision to sound and touch, and also supports action planning and language. But I think if you think of perception as being that whole problem, right, of how do you go from sense data to the whole world of thought, nobody has the answer to that. But I think the kind of tools you're starting to see here are really promising there. I think they're the best tools that we have, at least that I know about, for trying to get to the real problems of perception and where perception actually turns into cognition.
Okay, thank you.
I think we have time for one last question if it's very efficiently phrased and
we'll
very efficiently answered.
Thanks. My question is about analogy and sort of transfer learning. So I'm it seems like people are able to quickly constrain the space of metaprograms by using analogy to other things that we understand. And I wonder if you've experimented with kind of analogies or transfer learning from a totally different sort of program space into a new one.
People are experimenting on that. I don't know if you want to. Well, I mean, so for example, the graphics programs that I talked about at the end of my part, the hand drawing programs that Kevin Ellis talked about. If you look at his paper on Archive, he actually uses this thing to drive certain kinds of analogies between simple drawing programs. I know that Noah Goodman has looked at things like analogies in the context of learning simple kinds of programs. I think in the neural programmer interpreter space, there's interesting kinds of analogy learners being looked like. If you search through the iClear papers for this year, you'll see lots of interesting anonymous contributions of program learning. It's really inspiring, and a couple of them are starting to explore things like analogy. So I think it's a really good idea. I don't know that there's any really canonical examples of it yet, but do you want to comment?
Just say that hierarchical Bayesian priors over programs gives another approach that one could start to pursue, and that some work on that has been done for the automated statistician type case, where you try to learn, higher level variables that link many different time series.
There's also, again, to speak up for AI very generally, there's a tradition in AI research that almost never shows up at NIPS of people looking at structure mapping or other kinds of, the study of analogy is one of the old great topics of AI, and it's when we look at how might we build learning systems that really capture all the motifs of the activities of programming, analogy is one of them, and there are probably techniques which don't show up at NIPS, but yet we ought to draw on. And that's what makes NIPS so exciting, is that you never know. Well, what's going to show up at NIPS in 2 years. It's whatever isn't here now, but can be used to address some of these exciting questions. So by all means, check out analogy. And I guess right now we should go check out the opening remarks, right? Okay.
Thank you both for being very, very efficient. And I think we should all thank Josh and Vikash for an absolutely fantastic tutorial. Don't forget the opening remarks at 5 in Area A. And will both of you be around all week?
We're here all week.
They're here all week. Thank you very much.